So the last few videos, the last 3 videos have been focused on business applications of rates, business applications of derivatives. Derivatives are just rates of change. This video shows some other real-life examples of rates of change in derivatives. So example 4 says that you can estimate a tree's age in years by multiplying its diameter, measuring that in inches, by its growth factor, which is some number that depends on the species, but most species do have this linear growth factor. According to the Missouri Department of Conservation, the growth factor for a cottonwood tree is 2. There are no units here because we're going to answer that later. So letter A says, suppose that you find a cottonwood tree in Missouri that's 6 inches in diameter. How old would you estimate it to be? Well, we'll just use the information that's in the problem. Can estimate a tree's age by multiplying its diameter in inches by its growth factor. Okay, so we could say age is roughly its diameter times its growth factor, whatever you want to call that. DK. All right. If you wanted to write it as a function. So here, age will be its diameter in inches, which is 6. And its growth factor, which we said was about 2, 12. And the age is in years, about 12 years old. Approximately. Letter B says, what are the units of this growth factor? Now, there's a couple of ways of seeing this. One of the ways of seeing this, and this is a very kind of chemistry point of view, is that age, which is in years, is equal to the diameter in inches times the growth factor. What does the thing have to be in parentheses so that the equation holds true? Equations and all these things that we do with numbers really go with units too. And so what we really can do, and we haven't talked about this very much, is we can divide both sides by inches. To get that our answer, what needs to go on the side of the parentheses is years per inch. That's one way of approaching this. The growth factor says, with every inch of diameter increase, we think the tree will be about 1 year older. Another way of looking at this problem would be to look at it less mathematically and more situationally, okay? The growth factor for a cottonwood tree is 2, right? Which means that every time the diameter increases by 1, the age increases by 2, okay? Then again, you can get years per inches that way as well. A few different ways of approaching this problem. This is the method that works the best for me. Equations and stuff all have to do with, the units have to equal each other. Is this a derivative? Letter C. Well, a derivative is just a rate of change. Yeah, this is a rate of change, right? So how do the years change? How does the age change in years with how the diameter changes? Yes. It doesn't look like a derivative. We're not really doing calculus here, right? All we've done is just multiplied 2 numbers together. But rates of change are derivatives. Okay? This is a rate of change. You can see that it's a derivative a little bit more clearly if you looked at what the graph would look like here. As we increase the inches, like the diameter, right? Diameter in inches, that's our input. Our output is the age in years. And we're told that the growth factor is 2. Every time that we increase by an inch, the age goes up by 2. What is the slope of this function? This is the function, by the way. Age is equal to 2 times diameter. What's the slope of this line? It's 2. Slope is derivative. What are the units of this line, right? The units of this slope is rise over run. Rise is in years. Run is in inches. So the slope is in years per inches. That's another way of seeing where the units of this growth factor come into play. It's all kind of tied together. And of course, it's maybe a silly example to try to use calculus for, because it's very simple calculations. But it just shows how we can fit the language of calculus into ordinary things. Now, sometimes that's overcomplicating things, but a lot of times when we can fit the language in like this, even though a lot of times it's just simpler to do it other ways, a lot of the beauty and power of calculus can be applied. We're going to be seeing that later on in this chapter. But for now, we're just kind of playing around with these definitions and seeing how we can fit the language and definitions of calculus into some more ordinary situations. Example 5 says, if we look at the length of the day, hours of daylight, in Seattle, it's a function of the day of the year. Okay, if you ever look at a graph, it kind of looks like this. Okay, we got winter solstice over here, we got summer solstice over here, or it might be slightly offset. I don't remember, but it's basically that. I remember seeing something about it, maybe being offset. I don't remember. But anyway, on August 12th in 2012, there were about 14 hours and 24 minutes of daylight. In Seattle, August is summer. Yep, we're in the northern hemisphere. That checks out. And we're getting closer to the autumnal equinox, when the day and the night are both 12 hours. The days are decreasing in length by about 3 minutes per day. When you're in August, you're losing daylight every day that goes past. It's kind of sad. But if you're in August, you have so much daylight that maybe it's a good thing. All right, so find and interpret the value of the derivative of the daylight function. Well, if let's say f is the daylight function. Let f of x be daylight minutes. Minutes on day x. So we know, right, that f of, I don't know, August 12th, x doesn't have to be a number. X can be other things. But technically, we should put like what day of the year it is. But roughly, informally, f of the function value, the daylight minutes on August 12th, is going to be 14 hours and 24 minutes. So how many minutes is that? 14 hours is this many minutes. 24 minutes. This right here is optional. I just am describing some things. What the problem is really asking us to do, interpret and find the value of the derivative. So how is this function changing on August 12th? How the function's changing is its derivative. How is the daylight changing on August 12th? It's decreasing by 3 minutes every day. That rate of change is -3. Okay? The amount of daylight is going down. What are the units of a derivative? The units of the function, daylight minutes, per units of the input, just day. We're losing 3 minutes a day of daylight. Okay? So that's the derivative. And again, our interpretation is just this red underlined part. Right, we're losing 3 minutes per day of daylight. That's how we can incorporate this into the language and form of calculus. NB does something very similar. I'm recording this video on January 16th. I made the notes on the 15th. It almost worked out. It is wintertime in Seattle. There were about 8 hours and 52 minutes of daylight. But good news for everyone who has experienced a winter in the Pacific Northwest. The derivative is positive now. We are gaining 2 minutes every day. So similarly, the derivative on January 15th of daylight, how the daylight was changing, is +2. Again, we're gaining 2 minutes per day of daylight, which really doesn't seem like very much. You get like an extra minute in the morning, an extra minute at night, but it adds up. All right. And again, we have that like if you actually look at the daylight function, right, you have that sinusoidal thing. So it doesn't change that much near the solstice, but it is changing the most kind of around the equinox. All right. That's what we got here. A lot of different ways of incorporating derivatives into real life examples and how to just kind of use that notation, use that language, use those definitions. And in the next section, that's when we're going to start really calculating derivatives. How do we actually find these slopes? How do we actually compute these functions? That's what the next section is all about. But for now, enjoy some applications. Bye-bye.